Okay, so yeah, great. Welcome everybody to our session in the Merit Theory channel. Today our session is in a different day, but usually it's on Thursdays. But anyways, today I'm very excited to host Mufan Li on this topic of neural network scaling limits. Let me give you a small pedigree of our guest speaker. Mufan Li is an assistant professor in the Department of Statistics and Actuarial Science at Waterloo University. Previously, he was a postdoctoral research associate at Princeton University, and he obtained his PhD at the University of Toronto. His current research interests are in deep learning theory, in particular, scaling limits of neural networks. So without anything else to say, go ahead, Mufan.
All right, thank you for the introduction and invitation. Yeah, like I'm really happy to be giving a slightly different kind of talk than usual. Today will be mostly relatively high level and try to be as introductory and as possible. And I will also be trying to a slightly different kind of format. Will be writing along on my iPad instead. So as you can see, a lot of these are handwriting, so feel free to interrupt and ask me if any of my handwriting is not clear. And yeah, I will also leave some pause, try to remember to leave some pauses for questions as we get them. Okay, so yeah, so let's start. So the first thing I want to show you guys is essentially today's neural networks are large. And by large, I mean essentially everything within the computing power in using neural networks are large today. So this is a figure that is, I think, relatively well disseminated by this point. So this is from the GPT-4 technical report, where what they have found is that not only if you make your models and computing resource larger, you tend to get better performance, but it tends to be a consistently better performance. So let me just write it. So this is consistently better. So this is very interesting, first of all, that it is even better, but it is consistently better as well. And sometimes this is called scaling laws, and this will be related to the subject of study that I'll tell you guys about. But before we get there, I do want to briefly emphasize that OpenAI has not released exact scale of computing resource they have used for GPT-4, so we can only speculate. And the speculations are already pretty interesting, pretty wild, I should say. So the number of parameters, roughly speaking, the depth of the network multiplied by width squared, roughly speaking, is estimated to be around 1.8 trillion parameters. And the number of tokens being used is roughly 13 trillion tokens, that's roughly equivalent to 1.6 billion data points. So these are, each sequence is a data point with 8,000 tokens as the sequence length. So this is roughly the speculation of the size of neural networks that we're dealing with today. And the reason why I highlight this is that scaling limits is essentially the study of infinite size neural networks. And we are very much in the regime where asymptotics are the appropriate approach to model neural networks, right? Everything is big, right? The number of parameters is big, the number of tokens is big, the number of iterations that you take to train the neural network is big. And it's so big that asymptotics is actually going to be a very good and going to be a model for the neural networks. So there are several questions that we can ask from here. And essentially, the main thing that I really want to bring up here is, can we study infinite limits of neural networks? Okay, and here I highlight once again infinite, here, right? Obviously, all neural networks in practice are finite. So the infinite limits are meant to be a mathematical model of neural networks. But what are we exactly modeling here? So in particular, quantities going to infinity I should say include, so not necessarily all of them can be studied at this point, but the first most common quantity that is being studied is the width of the network. So in MLP is, for example, in a very straightforward neural network, the width everybody understands is the number of hidden neurons or per layer. But in some other settings, the width can also include, for example, in convolutional neural networks, the number of channels. Right? So number of channels is the appropriate notion of width. And when you have multiple heads in transformers, this number of heads is also an appropriate measure of width. So it's not just the dimension of each head in your attention. And it can also be the number of experts, if you have a mixture of experts model, etc. But so it can include a number of different things. And you can study essentially all of the variants, right? You can take number of channels to infinity, number of heads to infinity, you can take number of experts to infinity, or the dimension per expert or head to infinity as well. You can study pointedly as well. So just referring to, broadly speaking, these are quantities that can be large in practice. So we should consider them to be taken to infinity. And the next thing I also want to mention is the depth of the network also tend to be very large, right? So we call it deep learning because the neural network has very large depth. And just to say the number of depth can also refer to residual blocks. Right? So it can be residual blocks as well as a number of like more conventional notions of layer. Furthermore, as I mentioned above, the number of data points, right? So this is kind of like tokens, right? Tend to be very large. We're speculating GPT-4 is being trained on, 13 trillion tokens. Right? And as you guys, some of you may already know that in practice, it's very common to scale the number of tokens along linearly with the number of parameters. So chinchilla scaling recommends 20 tokens per parameter, for example. And then you train them in one pass, which means the number of iterations is also growing along with the number of tokens as well as the number of parameters. So training iterations can also be very large. I should also mention that you can also increase batch size as you increase the number of data points. Okay, it's training iterations. And obviously, this all training iterations can include obviously the number of steps, but other things that can scale are, for example, a step size schedule, like learning rate schedule, can also scale, right? So because perhaps you want a slightly different kind of step size decay when you have taken a lot of number of steps, but roughly speaking, your total flops is proportional to width squared multiplied by depth. That's roughly the total number of parameters multiplied by batch, which is the number of data points, and then multiplied by number of steps that you train. So in altogether, in an ideal world, we would like to study all of these quantities going to infinity, right? So the answers to this question is, yes, it is possible to study this, but it's hard. So what we can do instead, we cannot understand all of these things going to infinity at the same time. So instead, what we do is we try to understand what happens when some of these quantities go to infinities first. In particular, the way I listed them is actually in the order of technical difficulty. So in the sense that we understand the most about infinite width limits, and we understand slightly more about infinite depth limits, and almost nothing about infinite data and number of training steps. So this is kind of the regime where we're currently at, where the difficulty kind of increases as you go down this, as far as our current understanding goes. But I will say that even despite the limitations of the theories at the moment, which there are a lot of, there already, I should say, exist many useful consequences. Yeah, so basically what I want to say is that the math is hard, but we can already do a lot of very nice things with the math. And then today I want to show you a few of these things. So the first advantage, I guess I want to say, is numerical stability. And I'll explain what I mean by numerical stability in just one second. So we're going to consider, for now, for simplicity, it is just a one hidden layer MLP or neural network fully connected layer. So we're going to have a matrix W1, some nonlinearity, phi, and then W0. So for simplicity, we can just consider this is 1 by width, and this is width by some input dimension n0, and then this is n0 by 1 column vector. And all your weights are initialized with some IID random variables. You can actually choose sigma squared here if you want. In fact, I think PyTorch defaults this to be 0.02. And I'll show you that is somewhat arbitrary. But so this is basically like a very simple toy model of something that you can get in PyTorch. If you try to set up by default a one hidden layer neural network, this is kind of the setup that you get at initializations before you even train it, right? So there is a problem, is that what happens when you take the width n to infinity, right? So this is a very interesting question, because we do want our neural networks to be big, but immediately we actually already have a problem. Is because if you rewrite our network output as a summation, right? This is summation, let's say, over I from 1 to n of W1 I phi of W0 I transpose X. You see that we're actually summing over an infinite number of objects. So this is infinite eventually, infinite sum. So what do we expect for when we summing over infinitely many objects of the same size? Is that it actually explodes. It goes to infinity. In particular, to be more precise, the variance goes to infinity. So I saw a question, doesn't the initialization follow Xavier or other methods? Yeah, so you can choose, actually. So this is what is considered the standard parameterization. So it doesn't necessarily follow anything. But if you load up PyTorch, you can now choose certain parameterizations. And I believe at the moment, there currently doesn't exist a lot of options that I think what the theory would prescribe. But I'll explain that in a second as well. But you see, but I guess like I want to emphasize here at one point is very quickly is that the naive way of scaling up neural networks already leads to numerical instability. So right away, whatever the PyTorch default is, right? You have to be very careful choosing it to set your neural network up, because you already lead to numerical instability at initialization. This is before you even train anything. So if you take a step, and you're gonna see a lot of nets in your training if your width is too large. So what is the solution? There's actually a very simple solution, is that you scale down the sum. And we're actually going to scale down by exactly a factor of square root of n. And you notice that if we scale down by a factor of square root of n here, and observe what are the terms in the sum at initialization, these are IID zero mean random variables, right? So these are IID zero mean random variables. This is very important because central limit theorem tells that this scaling, if you have an infinite sum of IID zero mean random variables, but you scale the sum down by 1 over square root of n, this limit converges to some Gaussian process where a Gaussian random variable, but I'll just briefly mention that it's a process because you can consider this as a function of your input. And I won't exactly explain what this is, but this is some covariance kernel. So the short version is that this is now stable, right? So this is now stable. So basically, very quickly, by looking at what kind of limits the network converges to, you can very quickly understand that what is the best thing to do, what is the scale that you need to prescribe your neural network, such that you can still maintain numerical stability no matter how large you make the network. This is very possible to do if just doing a little bit of mathematics, basically. So I just want to show you a very straightforward example. But you can in principle do this for almost any architecture and any scaling that you want, and any training algorithms that you want as well. So this is just one of the simplest examples that I can show you. And the next thing I want to mention is that this math does extend to multiple layers. In particular, Li et al. In 2017 introduced this notion of neural network Gaussian processes. And that's exactly what it's referring to. So you don't have to just do one layer, you can do multiple layers. And so I also want to say that this type of a simultaneous limit, what I mean by simultaneous limit is that with n is going to infinity, but the prefactor 1 over square root of n is going to 0. And this is at a balanced rate, right? So this is exactly the rate that gives us central limit theorem, right? If you go too fast in either one, or too slowly in either one, you're not going to get a behaved limit that's exactly a Gaussian. You're going to get either 0 or some infinite variance object, right? So this is very important that you take these two simultaneous limit at a balanced rate. And this is what we call a scaling limit. Right. So taking a very brief step back, we want to study infinite-sized neural networks, but because things are going to infinity, we need to scale them down. So therefore, this is a scaling limit. And the takeaway here is that the analysis of scaling limits yield numerical stability. Do we have different types of prefactor for layers of different widths? Yes. So sometimes people call this either the fan-in or fan-out scaling. So you either use the previous layer width or the layer width afterwards. And I'll also show you that a different scaling for just the output layer in, I would say, 10 minutes or so as well. So yes, different layers can be scaled differently. All right. So the first thing that we found is that through a very simple calculation, we already realized that by studying scaling limits, we can understand which type of scaling is numerically stable. And we can prescribe, actually, solutions to fix numerically unstable limits as well. So the second thing I want to show you guys, this is something that was very surprising to a lot of people for a long time. But the second advantage of studying scaling limits is a theoretical understanding of a phenomenon that was highly surprising. Essentially, neural networks being capable of overfitting anything, right? In fact, it was known that it can overfit noise as well. But how can such an object that has the capability of overfitting anything generalize to unseen data? Overfitting should be, in a sense, a negative phenomenon you observe in a very complex model. But this is not the case in neural networks. And the phenomenon was understood actually using this scaling limit, what we call the kernel limit, essentially the Gaussian process limit. People have found that essentially bias variance has a relationship that does not directly trade off. Do not directly trade off. Right? If you look at a lot of the statistics textbooks today, there's a notion of bias variance trade-off that if you make your models more complex, you're supposed to overfit, and that is not good for your test error, which is in this case your test risk. But what's actually people have found is that, as you guys can see in this figure here, if you keep going towards the right here, right? If you keep going towards this direction, right? You can actually notice that your test performance actually starts to improve yet again. And neural networks always operate in this regime. And it's more modern interpolating regime because in training, neural networks can overfit any training data. You can drive training error to 0 on any data set, as long as your neural network is sufficiently big. So I won't go into too much detail on this. I just want to say that this, for a long time, was perhaps the main motivation of studying any sort of theoretical results of neural networks. And this has yielded the first, I guess, understanding of what potentially is behind the mechanism of benign overfitting, is the phenomenon that people say, or call this also double descent, as your risk can actually go down twice as you increase the capacity of your model. So I won't go into too much detail once again, but this is I would say, consider a very significant conceptual understanding of statistics for the whole community. All right, but there is one problem with this regime, is that there is no feature learning. Now, I'll define feature learning for you guys, but as far as we understand that, even in practice, we understand feature learning is a good thing. You want to learn good features. And even going back as early as, the ImageNet days, people understood that learned features is much better than human engineered features, right? You cannot handpick features to be nearly as competitive as features that are learned by the neural network. So you want the neural network to learn features. So in this case, what is this features that's being learned? So this is essentially this is the top 2 principal components of what I would call the penultimate layer. So the second last layer.
Probably you mean principal, right? As in PCA.
Principal, yes.
Okay.
Principal component, yeah. Yeah, so this is the piece, basically the top 2 components of the PCA that you get. And in this case, The left figure here is an infinite width network. And the right figure here is width 64. So this is something interesting to observe here for 1 second, is that the left figure here, the infinite width network, is supposed to have much more computing power than the right figure, which only has width 64. But somehow the top two principal components actually contain way fewer information. Right? So this is very interesting because somehow taking the network width to infinity lost us a desirable behavior, right? So this ability to separate these two types of data, the state and the city here, right? So in this paper, very nice paper here by Greg Young and Edward Hu. So this is sometimes called the Tensor Programs 4 paper. So I'll go into a bit more detail in 1 second. But this is a very undesirable behavior. And this is something that we want to fix, because no matter how big the network that we are training, we want this network to learn features. There are some more theoretical results actually explaining why this is potentially bad, but also won't go into too much details. Besides, I want to emphasize the fact that this is something we want to fix. This is not the right way we want to scale neural networks, right? So we can understand, for example, once again, through scaling limits, that if you scale the network this way, you lose a desirable property. So therefore, you can fix it. You can now, once again, leverage the understanding of what kind of scaling limits you end up at to study how to resolve this problem. So here's some intuition. So we have some network. So you can think about this as the output. You can think about this as a hidden layer. This one hidden layer network, once again, will be okay. And so this is the update per step. So we want to say, I just want to show you guys how much update do you get per step, per neuron. You can imagine for one single hidden neuron. And roughly speaking, the order of the update is 1 over square root of width. What does this mean is that the amount of update is actually going to 0. So this is vanishing. Not that contribution doesn't lead to anything useful, but that's a much more subtle point that I won't go into. But essentially, this is what led to the diagram above, and I'm just scroll up once very quickly again. So the left side picture is basically what happens when the width goes to infinity, is because per step, your hidden neurons are not updating enough, right? So this is basically what is happening here. So this scaling leads to the fact that we understand that hidden neurons are not updating enough. So how do we fix this? Intuitively, it's actually very straightforward. Well, it's not updating enough because the weights beforehand is updating too slow. So intuitively, if you can rescale the network somehow in a way that you update the weights in your earlier layers faster, you should actually fix this problem, right? So that's essentially the intuitive picture here, right? So if you change, once again, just let me emphasize this: if your neurons are updating too slow, right, has vanishing updates, you want to update the weight matrices beforehand faster, so that the neurons are actually updating at the correct rate. So this leads to a slightly different scaling called mean field, or also known as mu-p scaling. And I'll explain what this means in 1 second. So let me just briefly say, so this is the Gaussian process limit. And usually we use the scaling 1 over square root of n, 1 over square root of width. And the learning rate we use is actually constant. Right, so use constant linear. So this is a scaling that we know is numerically stable, gives us Gaussian process limit, and it's nice. So what does the mean field scaling do? So first thing first, we're going to do something a little bit strange. We're going to actually use 1 over width over here, and we're going to scale the learning rate by a factor of width. So let me just briefly explain what is happening here. So eta 0 here is just a constant, so you can ignore the eta 0 if you choose to in terms of scaling. We want to make the weights update faster. So update faster, right? So okay, so this is great. We want the learning rates to update faster, right? Because previously it was updating too slow. So now we increase the learning rate. So we know that this is exactly the learning rate such that it updates faster. However, what is the problem when you naively just increase the learning rate? You guys probably encountered this in practice before, is that you're actually losing numerical stability when you increase the learning rate. So simultaneously, this downscale of 1 over n, 1 over width in the front, is actually for numerical stability because you're updating too fast. And you actually kind of want to balance things out a little bit. And another way to think about this is that the updates for your output layer, so this update is good. Update speed is good. So this update speed is correct, is what you want. You don't want to change the update speed of the output layer. So what we want to do is you only downscale the output layer such that it offsets the effect of learning rate increase across all layers. So you downscale this, downscale for stability. Now you can do a little bit of math exercise for this if you want. Well, we can do this in another session, but this is the rough intuition here, right? So you want to increase the learning rate to make sure your weights are not updating too slow, but you're going to downscale the output for numerical to also once again maintain numerical stability. So this is what gives you feature learning in one hidden layer neural networks. And I briefly want to flash there's 5 separate references that roughly figured out this scaling at the same time, albeit it was a bit later that we understood why this was different. But this sometimes good ideas never show up by itself, and I want to show that there are 5 different groups that have done this at the same time, roughly. This does extend to multiple layers. Via something called the maximal update parameterization. So you can use the acronym MUP, or the authors decided that you want to use a Greek letter mu to represent MUP. So this is by, once again, Yang and Hu in 2021. So this is the Tensor Programs 4 paper as well. So this is the extension that you can do to multiple layers, and I actually want to briefly give you an overview of what this looks like. So very quickly, the left-hand side, what we have is the Gaussian process, or sometimes called the neural tangent kernel parameterization. Or maybe I'll just spell this out. So neural tangent kernel. I don't think I'll have time to explain what that means, but if you see this term, what it means to be a neural tangent kernel parameterization. So this is what the left-hand side is. So here's to notice is that before every layer is 1 over square root of width, right? It depends on the next hidden layer, right? So this is the kind of scaling that you want everywhere. So I'm just going to highlight this part, as well as the learning rate is constant, right? So this is constant learning rate. I just saw a very good question, so I'm actually going to pause to address this. So maybe I'll have other questions first as well. So why would the neurons update slow in the earlier layers? So This is a very subtle effect of the scaling that you use in 1/√n. I don't think I'll be able to go into detail in this, but essentially, if your network in a weight matrix has infinite input and infinite output, and sometimes an infinite by infinite matrix, this scaling, the naive scaling using Gaussian process, leads to this. If your output layer, because your output is finite dimensional, that layer of weight matrix does not suffer from this. But if you're somehow to increase the output dimensions, you will actually get the same thing. So it's a bit of a, it's very subtle. I think that perhaps I won't go into too much details here. But another question I ask, with these modifications, why would scaling limits still give us insights into finite neural networks? This is a very good question because, as I mentioned in the beginning, right, neural networks today are big, right? You know, we're talking about 1.8 trillion parameter models. Right. For lack of better words, 1.8 trillion is not very far from infinity. Is basically, like, I don't know if you heard the joke with the statisticians, 26 samples is essentially infinity that you plug in the central limit theorem, right? But it's not completely wrong in the sense that you can't actually give non-asymptotic guarantees on how far away you are from infinity. And there are guarantees for central limit theorem, for example, that says that usually you can give a very crude bound of even less than, like, with 100 samples, you can multiply, you can roughly be very good if your third moment is not very big. So if your third moment is like roughly I think 100 samples, make sure your Kolmogorov distance less than 0.05 or something like that. It's a very good approximation already. So there's some things to keep in mind is that if it's, because our neural networks are big, this is why the infinite sized neural networks is a very good model. Right. So I want to come back to this now. So once again, remember that so the neural tangent kernel or the Gaussian process regime use 1/√n as the prefactor, and the learning rate is constant. Right, so this is the part I want to highlight. So the mu-p scaling does something, does a very small modification. So we're going to let the output layer be downscaled to be 1/n, right? So once again, output is downscaled. And then we're going to upscale the learning rate, right? So this is exactly the same thing we have done beforehand for the one hidden layer case. So we're just going to leave the middle hidden layers the way they are, except the learning rates that we're going to modify across the board. So this is a global learning rate. Okay. So this is now, so basically update faster. Right. So this is the same picture as before. All the previous weight matrices are being updated too slow. Right. We're going to want to increase the learning rate to update them faster. And the output level is only downscaled to maintain numerical stability. And in fact, you can try these. I hope you can try training a different scale. And you will notice that this is going to be necessary as you increase the scale of the network. Actually, quick question in here. How much time do I actually have?
Well, I think 20 minutes, but we could extend for a bit more.
Okay, so that should be plenty of time. Okay. So the third advantage, which is probably actually the most significant advantage I want to actually highlight to you guys by using this scaling, is something called hyperparameter transfer. So on the left-hand side, this is something that you guys are probably familiar with, is that, well, for each network, you want to find the best learning rate, best hyperparameter to tune this. A learning rate is probably the most sensitive hyperparameter. And then you do the sweep, and then you get, for example, one of these curves, right? That's like on the left-hand side for each scale of the network. But the problem with this is that, okay, you find the best learning rate for width 128. Now you want to try this, plug this into width 256, for example. So, somewhere over here. And then you figure out that, okay, well, the best learning rate for, 128 is not the best learning rate for 256, which is over here, right? So there is this shift from the right-hand side to the left-hand side, right? And then it keeps shifting as you increase the width, right? It keeps shifting left. So learning rate, like, has to, the best learning rate has to decrease. In fact, if you look at it here, the learning rate is not even stable, right? So the best learning rate for width 126 is not even stable for width 512, right? So once again, right, so there's a sense of numerical stability that also shows up here as well, right? So if you naively scale up the network using the same learning rate, you can be numerically unstable as well, right? So this is something that we can definitely fix here with scaling limits. So this paper by Greg Yang et al. In collaboration with people at OpenAI have essentially figured out that turns out if you use the mu-p parameterization, your learning rates, your best optimal learning rates are actually the same. You see the best learning rate here is the same here, is the same here, is the same here, and maybe it gets a small shift towards the end, right? You see like a very tiny shift maybe at most, but it's very consistent. And even despite the shift, this is a very good learning rate still, right? If you use the smallest network to find the best learning rate, you can transfer it to the biggest network, and now the network size, if you look, is almost like 100 times different, right? So it's like almost 80 times difference. So almost 2 orders of magnitude difference here. And then you can still use the same learning rate. Now that's a huge computational saving because, well, you're only searching the network once, right? So if you were to take anything away here, it's like only search hyperparameters once on a small network. Right. So this is a huge computational savings, right? Because you only have to train, anytime you have to train a big model, more than once, we're talking about, like 1.8 trillion parameter model. This is, probably hundreds of millions of dollars to do one of these training runs, right? You're not going to do this twice, right? So you can only afford to train the big model once. So you want to do as much study understanding of what are the best hyperparameters you can as possible to make sure your big run is the best. Right? So this is basically one of the things that you can do, and it's probably one of the most sensitive things that you can tune is the learning rates here. But the second thing I actually want you guys to observe here is very subtle. I don't think this is highlighted enough. I know Greg Yang has mentioned this, but in his work, but I don't think it's highlighted enough in public. Is that notice that the loss is improving. Is improving consistently, in fact, as you increase the size of the network, right? So this is not fully understood, but if you look at here, right? So this on the left-hand side, these two losses are actually about the same. So when you double the width from 4,000 to 8,000, or in fact, even from 2,000 to 8,000, you quadruple it, you're actually roughly at the same loss. But this is not the case using mu-p at all. So this is a bit subtle. I don't think we fully understand theoretically why this happens, but that we do know for a fact that if at least empirically, that if you do not scale properly, that you do not always get your performance of the models to improve, right? So I mentioned that earlier. There are a lot of scaling law works that suggest that if you tune everything properly, your loss should always improve. But if you don't scale properly, that's not going to be the case. So you have to actually always find an appropriate scaling such that the loss improves. So this is something very subtle that in practice also very important because, well, you don't want to be quadrupling your computational budget just so you get the same loss, right? So this is and you want every time you want to fire off a big experiment, you want to make sure that you get better performance. So this is something very subtle. So I do want to highlight this part here as well. So the loss does improve here. All right. In the rest of this, I do want to also briefly mention some other types of scalings. In particular, the community has made some progress on infinite depth scaling. So I want to briefly mention some things here. So in particular, there's two types of infinite depth scalings. And I just want to highlight this first one using residual connections first. So what does it mean to have a residual connection? Is that, well, you're going to first copy the previous layer over. So if you look at in your most normal conventional MLP blocks, all your hidden layers are going to go through the activation function, go through the weight matrices. This is no longer the case, right? So we're going to have this part here. This is in some sense skipping, right? So this is a skip connection, right? So it does not go through any activation functions or weight matrices. And then you add your other typical MLP block, right? So this is basically what the ResNet proposal was. So I think this is kind of like well known at this point. Except if you do this, actually, it is not numerically stable. Once again, so what you actually have to do to make this numerically stable is you have to add a factor of 1 over square root of depth. So let me just emphasize this is a 1 over square root of depth downscale. Right. So this is now a common theme in this talk, right? So anytime you want to add too many parameters, you're going to get numerical instability if you do it naively. You have to always downscale the size of the network in an appropriate fashion so that you maintain numerical stability. Previously, if the width is too large, you downscale the weight matrices by 1 over square root of width. Now, if the depth is too large, we're actually going to also similarly downscale by 1 over square root of depth. Right? The square root comes from the fact that it's a central limit theorem scaling. Now, if you want to do something different, then you're going to use a different scaling. Right? If you're going to use large number scaling, it's 1 over depth, for example. Right? So this is just one possible scaling, and this was shown to actually also lead to hyperparameter transfer, which is great. And in fact, so we have, so I was co-authoring this paper on the left here with Bordelon et al. It we call depth-wise hyperparameter transfer. And so maybe I'll just highlight here. This is the depth-wise HP transfer paper. And is concurrent with another one of Greg Yang's paper that I call the Tensor Program 6, or depth UP. Question here for 1 over depth to the p are p only exponents you have seen studying in literature. It's a very good question, actually. So essentially, the short version of this is that there's only 2 regimes of the scaling. So we actually usually call this alpha. So in fact, let me do this now. So let me do this. Let me call this 1 over d to the power alpha. And then this is alpha is equal to 1/2 regime. Roughly speaking, I should say that instead of choosing alpha is equal to 1/2, you can also choose technically alpha within anywhere between 1/2 to 1, but not 1 exactly. And this regime roughly behaves the same in the limit. And essentially, there are going to be terms that vanish at a very small rate. And so they're kind of like, so the only 2 distinct regimes are alpha is equal to 1/2 and alpha equals to 1, which is the part that I'm about to explain next, is that in this case with transformers, and you can use Adam W with Adam W and sub different algorithms, we're going to choose 1 over depth here in this scaling, with alpha equals to 1, essentially. So this is this scaling. So these are the 2 distinct scalings. And the reason why is that, as we found out, that if you want a notion of feature learning or maximal update appropriately and lead to hyperparameter transfer properly, this is the only scaling that is allowing for this when you have multiple layers per block. Per residual block, I should say, per what we call a res block. So the multiple layers part is important, right? So if you notice here, if you notice in the first case here, this is only one, in some sense, one layer. But if you've seen the definitions of transformers, self-attention, or MLP blocks, it has at least 2 layers in each one of these blocks, right? So, and it turns out that this is the scaling that gives us the best hyperparameter transfer. And this math was also written here. I should highlight this paper on Day et al. 2015. So this is another paper we co-authored called complete P, so a complete parameterization, in the sense that are factors that needs to be satisfied to give us the best hyperparameter transfer properties. So that's a very good question. This is very subtle, and I don't think I have too much time today to go into the deeper details of this, but perhaps another talk. And obviously, you guys all feel free to message me privately as well. So I just want to briefly also highlight the empirical result that we get. This is also from the complete P paper. So yes, we get hyperparameter transfer across depth as well as width now, right? So you can see here that the best learning rates from the smallest model, even depth 2, actually transfer quite well to depth 128. And the other thing I want to mention here is very importantly is, once again, the loss improves consistently, right? So this is very, once again, very subtle, but it's very important that the parameterization leads to the loss improving as well, because this is, at the end of the day, if you want, once again, like if you want to fire off a big experiment, you want to make sure that the more expensive the experiment you are, it actually yields you the better performance that you want from it. Right? So this is some very exciting results that we have. We also have a ton of other results in this paper that I won't be talking about. So if you're interested, you can also go see this recent paper here. All right. The other direction that I also want to highlight here is also my research direction, is something called the proportional limit. So this limit doesn't use any skip connections. Well, it doesn't have to use any skip connections. So the scaling here in front uses a constant c here as well as the square root of width here. And we're going to use some constant c here. You don't have to worry about this too much, except that basically it normalizes the activation function scale in some sense. You can think about it as normalizing the activation function scale. And the main thing here is that the activation function needs to be a perturbation of the identity. Right? So remember, the skip connection reduces the effect of the activation functions by adding a prefactor, 1 over square root of depth or 1 over depth. We're going to do something similar, but we're going to do it only at the activation function. Because it turns out weight matrices are fine. The only thing that you have to downscale is the activation functions. So this is going to be square root of depth plus something on the scale of 1 over depth. And once again, you can imagine that this is downscaled. Right? So as you increase depth, you're going to want to downscale something depending on depth. And in this case, we're going to take, this is width and this is depth, right? Width, depth, go to infinity. And then we're going to need to actually maintain the depth to width ratio to be constant. So this is different regimes for many different reasons. Because not only because that the previous regime leads to, you do not need the depth and width to follow any ratios. You can actually go to infinity at any rate and it leads to the same limit. They're kind of decoupled, if you will. But in this case, the depth and width are very highly coupled. And you actually really need to study the joint limit at maintaining a proportional ratio. And hence, this is the name where it's a proportional limit. Right? I really do have to understand this. So I do a ton of work in this direction. So this is probably my main research direction in this regime. I don't have too much time to also talk about this, but I will just briefly mention that we can get very similar results. We can get numerical stability for Gaussian process results, that kind of stuff. For MLPs, for transformers, we can understand, in fact, a little bit of training dynamics now that's in some forthcoming work. And that will actually also yield hyperparameter transfer as well, but I won't talk too much about it. Yeah. So just to wrap up, I also want to talk a little bit about open problems. So I'll just address this question. Does the geometry of the loss landscape approximately scale with mu p? Yes. This is a very good question. I think the best way to give you an answer for this is that the training dynamics in mu p scaling is incredibly consistent at different scales. We don't have very good understanding of the loss landscape per se, with the exception of maybe the largest eigenvalue, so like just the sharpness of the loss landscape. I think I've seen some theoretical results on that, but roughly speaking, it is very consistent across. So for example, if you see some oscillations due to edge of stability, for example, at some smaller width, you'll see the same thing at a larger width, right? So in that sense, the loss landscape is very consistent. It does scale with mu p. All right, I want to briefly mention some open problems. The first thing I want to advertise is my own research. There's a lot of open problems in the proportional limit. And the first thing I want to say is the training dynamics. In the sense that, so mu p has a characterization of training dynamics, but the proportional limit currently does not. So I do want to figure this out at some point. Broadly speaking, large data and training steps are open. Very few works can study both large training data points and training steps. This is a very difficult direction mathematically. So there's a ton of open problems, and I have to say the closest we have towards this direction is a physics style kind of like non-rigorous paper that I saw recently that can only still study one hidden layer neural networks. So we have only very, very limited results towards this direction. Right? We have like nothing remotely close to studying realistic models, and definitely not close to being rigorous math for sure. So a ton of open problems in this direction. I want to say a significant part of theory is to also understand the algorithms and architecture we're using. So one thing we would like to do is compare algorithms and architectures. So the reason why is that, well, we want to understand why certain algorithms or architectures are better, right? And in practice, this is a very serious problem, right? People talk about why muon is better than Adam W for a long time now, and the best thing that people can do is to run it on a ton of experiments. And obviously, there's a ton of confounding factors. Is that do they scale to different sizes of the models? Do they use the same? Are they both equally tuned hyperparameter wise? How do they run on different types of slight modifications of architectures? What's the effect of like normalization layers on these? So ideally, we would like to understand a lot more about fundamentally why certain algorithms or architectures are necessarily better. Right. So as much as people think perhaps transformers plus Adam W is really good, we want to really understand why that is the case from a theoretical point of view, perhaps saving a ton of computing resources, running a lot of experiments, before to draw that conclusion. And the final thing I'll leave you guys with is that we would like to use theories to finally understand scaling laws. I think we're still somewhat far from understanding scaling laws. There are some papers on toy models that have yielded, I guess, important conceptual progress, but I would say we're still very far from understanding any realistic architectures for sure. So we don't understand why, for example, that is the scaling law necessarily like kind of like a real limit of of that we cannot break through, and is it a function of data, is it a function of architecture or training algorithms? So I don't think we fully understand this. There's only very limited progress in this direction. So these are just some, I guess, open problems that I think are very important that can be potentially answered by studying scaling limits in the future. I'll briefly address the final question here. So while infinite width and depth are motivated by instability, it's not clear the motivation for infinite data is that direction. Can you provide some intuition? Oh, this is a great question. So the short version is that if you do not take the data and training steps to infinity jointly with width and depth, the behaviors we get are not exactly the same. So if you go to our complete P paper, so this figure, for example, this figure is for fixed data and training steps, right? But the one I want to highlight is that, but it's different from, we get a different figure from, say, like the 20 TPP regime. So this is tokens per parameter. Tokens per parameter. So this just means that you increase the number of data points and training steps along with the number of parameters with width and depth at the same time. And what we have found essentially that, for example, this one yields a lot more flatter transfer curves. Yeah, you can see the paper for this detail, but basically the behaviors are different, and currently we do not have very good theory to actually understand what is happening there. Yeah, and in fact, as a result, we don't understand what is the best scaling. What is if you see numerical instability, or if the loss doesn't improve in practice as you increase the scale, we cannot tell you why at the moment. So this is the reason why I think it's very important to also study the data limit and number of training steps on it as well. What are the interactions between different optimizers and scheduler with respect to hyperparameter transfer and scaling law behavior? That's a very good question. So I don't think we have the answers to everything yet. But yeah, the different optimizers, I will say that there is a way to derive a feature learning scaling for every optimizer. That is very possible. So we know how to do hyperparameter transfer for each fixed optimizer and scheduler. Schedules actually transfer almost naively with learning rates. Batch schedules are more difficult. Batch schedules, as like I mentioned, is related to data scaling, so we don't really understand batch scheduling. So hyperparameter transfer can be done for each fixed optimizer for different hyperparameters that it contains and its own schedule. So that is possible, but we don't understand how to compare different ones. So this is one of the open questions that I'm leaving open at the moment, is that we want to be able to compare, for example, Adam W and muon. We want to understand why one is better or worse than the other. And in particular, scaling law behaviors is almost completely open. We don't understand whether or not a particular architectural algorithm should lead to better or should not lead to better scaling law behavior, or we don't understand either direction really. So that part I would say is one of the most important directions I think this theory can contribute towards, but yet we're still relatively far from. Yeah, with that, I think I'll just leave you at the open problems, but I can stay on the call for a little bit if you guys have any further questions. And I also want to, invite you guys to feel free to message me as well. But yeah, no, at this point, I want to thank you all for listening, and yeah, I'd be happy to answer any further questions.
Yes, thank you so much. Let me actually stop sharing.